Year 9, identifying curved graphs. Having plotted various different functions which result in curved graphs, both by hand and using Desmos, we're now going to discuss these in a little bit more detail and identify some of the key points relating to each type of graph. So the first graph that you plotted was the graph of y equals x squared, which looks like this. It's a symmetrical U-shaped curve. Now, we've talked about quadratic functions before and quadratic expressions. A quadratic will contain as its highest power of x a square or an x squared term. So this particular function is referred to as a quadratic function, and it results in a quadratic graph, which is also referred to as a parabola, spelt like this. Now, the graph is symmetrical. Think about why this is. If you take an x value of 2 and you input it into the function, your y value will equal 2 squared, which will equal 4. So you'll have a coordinate 2, 4. Now, if you input an x value of negative 2 into the function, well, your y coordinate will equal negative 2 squared, which will also equal 4. So your coordinate will be negative 2, 4. So because when you square a negative number, the answer is positive, you will end up with a symmetrical curve like this. When you're sketching it, be very careful. At the bottom of the curve, it doesn't flatten out. And it also doesn't have a pointy V shape either. Now, this point on the curve at the bottom of the U is sometimes called a turning point. You'll learn much more about this in Year 11 and if you choose to study maths at A-level. Now, a quadratic function can be adapted in many different ways. So, for instance, here, this is still a quadratic function because the highest power of x is a square, but there are other terms included as well. This is something you'll be exploring in the next lesson. Now, when you plot any quadratic function, you will get this U-shaped parabolic curve. The graph will always be symmetrical and there will always be a turning point at the bottom of the U. Now, one mistake people make quite frequently when they're calculating coordinates involves dealing with negative values. So let's choose x equals negative 2 as a coordinate and see what happens when we work out y. Y would equal negative 2 squared minus 2 multiplied by negative 2 minus 1. Let's work this out. So negative 2 squared is 4. Negative 2 times negative 2 gives us a positive 2, and then subtract 1. This gives us a y coordinate of 7. So if we follow up to the curve from negative 2, we can see that there is a y coordinate of 7. Now, because people quite often input this into their calculator without thinking and without including a very necessary pair of brackets here around the negative 2 before you square it, they quite often get the wrong y coordinates here. So think very carefully, use your calculator very carefully. And if you're dealing with a quadratic function and you don't end up with a symmetrical, smooth U-shaped curve, then you have calculated one of your coordinates or more than one of your coordinates incorrectly, and it's usually due to a calculator error over here. So be careful. If you're using a calculator, make sure any negative numbers being raised to a power are in brackets. So let's now have a look at the graph of y equals x cubed. This is a cubic function, and it has a sort of S-shaped graph like this. You can see that there are some similarities to the quadratic graph, but we don't have the reflective symmetry. The graph rises very, very steeply because when you cube numbers, the answers become very large. So for instance, if your x value is 1, your y value is 1 cubed, which is just 1. your x value is 2, your y value is 2 cubed, which is 8. X equals 3, y equals 27. As you can see, the numbers start to become very, very large. If you go up as far as 10, for instance, 10 cubed, we have 1,000, which would be a very, very steep part of the graph. Now, because when you cube a negative number, you get a negative answer, the graph will have a portion down here as well. So, for instance, if x equals -2, your y value would equal -2 cubed, which works out to be -8. It's interesting to take a moment to compare the graphs of y equals x squared and y equals x cubed on the same pair of axes, so you can see the difference in the level of steepness, and you can hopefully see that y equals x cubed is much, much steeper than y equals x squared after we reach this point over here. So at this point over here, that's the coordinate 1, where x equals 1 and y equals 1, which sits on both graphs. Now, after we hit this point, y equals x cubed starts to become much, much, much steeper, and you can choose a pair of coordinates just to explore this. So if x is equal to 2, then if we look at y equals x squared, that would have a y coordinate of 4. But if we look at y equals x cubed, that has a y coordinate of 8, so much, much higher. Now, if x is equal to 3, y equals x squared gives you a y coordinate of 9, but y equals x cubed gives you a y coordinate of 27, again significantly larger, which is why the y equals x cubed graph is much steeper than the y equals x squared graph. So next you plotted the graph of y equals the square root of x. Now, unless you're dealing with very specific x coordinates, which are square numbers, if you input, for instance, x equals 2 into your calculator, you will end up with a decimal value as your y coordinate, such as the nature of square roots. Now, the graph does continue to rise, but quite slowly. Now, this is quite an interesting aspect of this particular graph. So here's y equals the square root of x, but a number of you may have been wondering, when you square root a number, it's possible to generate a negative and a positive answer. So, for instance, if you take the square root of 4, well, that's equal to 2, but it's also potentially equal to -2. Now, if there is no sign in front of the square root symbol, we're just assuming that we're only taking the positive root. So here, for instance, you can see that it just says y equals the square root of x. There's no sign there, so we assume it means the positive root. I've also drawn the graph of y equals, and very specifically, the negative square root of x. So I've deliberately said here that we're going to take the negative value each time we take the square root. So, for instance, if we take this graph, y equals negative the square root of x, or the negative root of x. Now, if I decide my x value is going to equal 16, then if I'm taking the negative square root, then I deliberately want -4 as my answer rather than 4. So this produces all of the negative roots, which can be demonstrated by the green graph here. So there's y equals negative the square root of x. So if you pick an x coordinate of 4, we can either generate a y coordinate of 2 on the red graph, or we can generate a y coordinate of -2 on the green graph. Now, what you may have noticed is that the graph looks a lot like the parabola y equals x squared, except it looks like it's been rotated or turned. Now, there's an interesting reason for this. Let's take this graph here, y equals the square root of x. Now, an interesting thing happens if we square both sides of this. So let's imagine we square both sides of this function. The left-hand side will become y squared, and the right-hand side will become x. So this gives us the graph of x equals y squared, which is again a sort of parabola, except it's defined differently to y equals x squared, and that's why the parabola is rotated or on its side, as some people might like to describe. But it's a similar type of curve, and you can see the symmetry, hopefully, and you can see here that you've got a turning point at the bottom of the U. It's just that the U is sideways compared to how you're normally looking at it. Now, the last function that you were asked to plot was the graph of y equals 1 over x. Now, this is sometimes called a reciprocal function. Now, why is it called that? Well, for instance, if you're asked to take a number 2 and find the reciprocal of 2, well, then you would invert it, so you have a half. If you have 3/4 and you find the reciprocal, it becomes 4/3. Some people like to describe the reciprocal as calculating 1 over the value. Now, this particular type of function is also sometimes referred to as a hyperbola. Now, this is something that you will come across more in A-level maths, in particular in A-level further maths. Now, this is a really interesting function because it has two parts to it, or two branches to it, a positive section and a negative section. So you can see in this region over here, where x takes a positive value, your y values will also all be positive. In this region over here, your x values are negative and your y values will also consequently be negative. But the most interesting thing happens here at x equals 0, because at x equals 0, in theory, to work out a coordinate on the curve, you would have to work out y divided by 0. But this is undefined. It's impossible to calculate y divided by 0. Now, this means the graph does not exist for an x value of 0. It's impossible to have an x value of 0 for this graph. And we say the graph is discontinuous at x equals 0. Now, interesting things happen when x is a very small number, so let's say just above 0. So what would happen if we took an x value, for instance, of 0.001? Now our y value would equal 1 divided by 0.001, which comes to a value of 1,000. So when x is a value very close to 0, you can't even see it on this curve, the y-coordinate would be a very, very, very large number, in this case 1,000. And it's impossible to actually draw this on this particular set of axes. You could use Desmos and then zoom out very, very carefully to see it. But even then, that would be quite difficult to see. So that's why the graph looks so steep over here. And a similar sort of thing happens here when x is very, very small and very, very negative. So what happens when you try and divide 1 by a very, very small number? You get a very, very large answer. So the graph gets closer and closer and closer to this y-axis, but it never actually crosses the y-axis. So there's a mathematical word to describe this behaviour, and we say that the y-axis is an asymptote. That's the spelling there, asymptote. And the graph approaches the y-axis asymptotically. That means it gets closer and closer and closer to the y-axis, but it will never actually cross the y-axis because you cannot have a y-coordinate at x equals 0. There's no way of breaching that. So all that happens is the graph becomes closer and closer and closer. And why does it do that? Well, for this reason here. For when x becomes very, very small, y will become very, very, very large. Now, for this particular graph, the x-axis is also an asymptote. And you can see the graph gets closer and closer and closer to the x-axis, but it never actually reaches it. Now, why is that? Well, let's imagine that x takes a very large value. So, for instance, x equals 1,000. What happens when x equals 1,000? Y equals 1 divided by 1,000, which is 0.001. So it's a very small y value. Now, you can't even see that here. All you can see here is this coordinate where x is 10 and y is already very, very small at 0.1. So when x is 1,000, y is much, much smaller than that, 0.001. But you cannot ever get a y value of 0 because y is calculated by taking 1 and dividing it by x. It is impossible to find an x value that you can divide into 1 to get an answer of 0. It's just not physically feasible. So that means that y can also not equal 0, just like x cannot equal 0 for this particular function. Now, a lot of this is well beyond the scope of mathematics that you are required to understand at Key Stage 3 level or even at GCSE level. A lot of this is the sort of mathematics that you'd be discussing at A level, in particular in A level further mathematics. At the stage you're working at, you need to understand that this is called a reciprocal function and that it produces a graph with two separate parts to it, and the graph has a break or a discontinuity at x equals 0. So those are the key points that you are required to understand and know at this level.